So let's look at how these questions look like. Because the chain rule is so useful, they actually change the way the questions look because they can represent these huge things. So instead of a question like this where it says differentiate 1 minus x squared all to the power of 6, the question actually looks like this. It says use the chain rule to find dy by dx when y is equal to u to the power of 6 and u itself is equal to 1 minus x squared at a specific point. So the questions look more like what's in blue as opposed to just go off and use the chain rule on your own, because for the ones that you can do on your own, you already have a different rule. So I'll give you a second to copy that down. And it also allows us to tackle some of those crazier ones without having to write them all out. The other thing that's important is often because the chain rule is a differentiate of a huge function, we usually don't just say find the derivative. We want to find the derivative at a specific spot. So it makes the math even easier. And that's really the idea behind the chain rule, is making a complicated question easier by breaking it into smaller chunks. So one of the first things we can recognize is we're asked to find the derivative or the slope of the tangent at x equals -3. So what we can do right before we even do anything else is we know what the value for x is. So why don't we use it to find what the value of u is? And that's going to save us in a step coming up. So first we'll just go 1 minus and then -3 squared. So of course that's 1 minus 9, which is -8. So this is going to be a little bit easier when we go off and do the math in a moment. So if we're going to use the chain rule, and of course it stresses that we use the chain rule, so we're going to say dy by dx is what we're trying to figure out. We need to use the intermediate step of u, so dy by du, dot du by dx. And by using the chain rule, we've taken a question and broken it up into smaller pieces. So it's just plain old u to the power of 6. So if we differentiate u to the power of 6, it's just 6u to the power of 5. And then we differentiate u with respect to x times, and then differentiate this is what, just -2x. Now if this was find the derivative, we would have to substitute u back in and collect like terms and so forth. But because it's asking us to find the slope of a tangent at a specific point, we can sub in x right here and u, which we already figured out, right there. So it actually saves us a little bit of work. And so it ends up being 6u to the, so u is -8 to the power of 5 times -2 to the -3. And then I'll let you do this on your calculator. A couple of steps to make sure you raise 8 to the power of -8 to the power of 5 first, and so forth, and you should get an answer of negative 1,179,648 off the top of our head. So you can check that, pause if you need to ask around or ask any questions. But we'd like to move on to the next example. So here's the next example. Again, you'll notice that it says, this is part B, so we're using the chain rule to find dx by dy. This is a much more complicated equation if you could imagine what the original would look like, but it's broken up into smaller pieces so we can handle it a little bit easier. So again, it's asking us for a point at x equals 2. So let's use that to figure out what u is. And actually, since I've got a root sign here, we know one of the strategies that we've discovered in the last couple of days is to change these to x squared minus 12 or plus 12 to the 1/2. Because we know how to differentiate exponents to the 1/2, but we really don't have a rule for root signs. So we're just going to change that. Now we'll substitute that 2 So 2 squared is 4, plus 12 is 16, to the 1/2, which is the same as the square root of 16, which is 4. So that's going to be helpful to know that u is 4 and x is 2. We can sub that in when we get to that stage. All right, so we'll use the chain rule. So dy by dx, of course, we're using this intermediate step again. So dy by du times du by dx. It allows us to take a really big function and break it into smaller questions. So the first one is dy by du. Now, if you look at it, y is itself a quotient. And so we're going to have to use the quotient rule in the first part. But you can imagine that it's a little bit easier doing the quotient rule with a u as opposed to this whole big root sign being in there. So treat it like its own question. Derivative of the top, which is 1, times the bottom, which is u squared, minus derivative of the bottom, which is 2u, times the top, which is u plus 1, all over the bottom squared. So that is dy by du times du by dx. So now we're going to look at this function, and actually in this form is be best, and differentiate that. It's a power rule, so it's 1/2 x to the, bracket x squared plus 12 to the, and then subtract 1, it becomes negative 1/2. But it's a power of a function rule, so we have to then differentiate inside. So we did the outside, and now differentiate inside, and inside the derivative is 2x. Now at this stage you can simplify a little bit. So before I substitute in, let's simplify a bit. So 1 times u squared is just u squared, minus, we could do a little rainbow here, make my life a little bit easier. 2u squared minus 2u all over u to the power of 4. And life could be a little bit easier if we collect this term. 1/2 times 2 is just 1. So it's 1x, x squared plus 12 to the negative 1/2. Now we could collect like terms and have your u up there. That'd be fine. I think it'd probably be easiest. Anytime we can simplify, we should. So we've got, this would be negative u squared minus 2u all over u to the power of 4. This side, there's really not much more else I can do except for rewrite it. And then I can even simplify this now even further. Since everything is divided by, we've got a u, and u, we can divide everything by u in this part. This becomes a 3, this becomes a 1, and that's gone. So that will leave me with negative u minus 2 all over u cubed times same thing. Now, I mean, I took a couple of steps here to simplify my work, but I can substitute in these values for x and u at any time, because I know that x equals 2 and u equals 4. So I'm going to take these and sub them in to right here. But there's no rule that says you couldn't have subbed it in here, subbed it in here, or subbed it in here. Of course, any simplifying you can do before you substitute will make your math just a little bit easier. But I've got it down to this stage, so I might as well sub in now. So remember, from the top, u I figured out was 4, I think, right? Yep. So now wherever I see a u, I'm going to put in a 4. So it's negative u, so negative 4 minus 2 all over 4 cubed. And wherever I see x, let's just remind myself, x was 2. So I'm going to put in a 2 for every time I see x. And now I just need to simplify. Divide the top and bottom by 3 or 2, I think. (16 to the negative 1/2). Well, 16 to the 1/2 is the square root of 16. And the negative tells me to go on the bottom, so it looks like this. Oops. I'm getting down to some numbers that I think I can manage. Simplify this even further. And there is my answer. So if we stop and think about it, the calculus part of this question is, I think, pretty manageable. Of course, where it gets challenging and all the algebraic manipulation and substitution you have to do, make sure you don't make a silly mistake. I'll give you a second to look at the whole question in a moment, but I just want to make sure we understand all the recaps of the steps. We're using the chain rule to differentiate a pretty complicated function. The function's already been broken up for you into two separate smaller functions, the y equals u function, and then u equals something x function. So we differentiate each of them on our own. We know we're going to eventually substitute x equals 2, but to save ourselves some work, we can do that substitution here to figure out what u is. So we differentiate y with respect to x, and you see that it's a quotient rule, so derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And then we differentiate the second part, du by dx. We recognize it's a root sign, so we make it to the power of 1/2. That 1/2 comes out front, and we subtract 1 from the exponent, and then differentiate inside and get the 2x. All these middle steps is just simplifying to the point that you can substitute. And like I said, you can substitute at any point. When you substitute, you're going to substitute u equals 4 and x equals 2. Be careful of your order operations and you're simplifying to get down that the slope of the tangent is -3/64.